All right, folks. Well, it's 8 o'clock, and I'm going to go ahead and get started. I'm going to just start with a few announcements, um, which may or may not be that relevant. But I did originally pre-record the lectures today, but there was no sound, so I'm going to be presenting live. My idea is that I'll pre-record the lectures in segments, and that way I can be on the chat and answering questions during the lecture, and then we'll either way, we'll take a little break um, periodically. Today we'll have a break at about a half an hour, and then uh, this next segment's about a little bit over 20 minutes, and the last segment's a little bit under 20 minutes. Um, so we'll have these breaks that we'll take for me to stop and answer questions about each section. So you can go ahead and type your questions in during the lecture if that's what you want to do, or you can wait until I take the pause and I'll show my silly face instead of the slides again, and hopefully we can take care of questions. Okay. Eventually, this will turn up as a recording, so for folks who missed it, but also if you want to review it. Obviously, I started the recording right away, and so there's like 20 minutes of me staring off into space and occasionally typing in the chat. So I'll have to hopefully be able to edit that or put a note in there that you can just fast forward. So with that said, I'm going to go ahead and switch to the slides and get started. All right. So today we're going to talk about basic chemistry. And I'm sorry, I just wanted to. There we go. Again, that's part of just being able to understand certain processes that are happening in biology. We have to have some really basic understanding of chemistry. And we'll be talking a lot about, almost, probably not every lecture, but almost every lecture will involve some chemistry, right? But it's not too bad, I hope, and we really are just kind of scratching the surface with one lecture on it. But we're going to cover a couple different things today, but let's go ahead and get started with this first little section. Let's see, sorry about that. I opened this up in the wrong. Sorry, I apologize. I opened it up in the wrong application. There we go. And all right. So why there's lots of reasons why chemistry is important, but mainly it's because we want to talk about metabolism, right? And metabolism is the sum of all the chemical reactions that occur in a living organism. So these are going to be important for the function of the organism, for it to be able to do what it needs to do to be alive. And so because we have to talk about these chemical reactions for metabolism, we need to know this basic chemistry. So first, there's a couple of terms that we need to define. And we'll have several of these. So, again, you might imagine on an exam a multiple choice question where, the question is, matter is blank, or, something with a definition, and then I'm looking for the word matter. So, just as you do kind of look these things over, kind of do think about how they might show up on an exam. So matter is anything that occupies space and has mass. So we have to talk about what that is. It is the physical stuff of the universe, and it's composed of chemical elements. And these chemical elements can occur in three states: as gases, as liquids, and as solids. And depending on the conditions, they can make transitions between these different states. Mass is a measure of the amount of material in an object, or in matter for that matter, right? So it's just a measure of the amount. Usually we talk about in our daily lives when we go to the grocery store, we might think about pounds, but in science we like to talk about, say, metric units, so grams. We're going to have, since we're talking about chemistry and kind of down at the smaller level, we're going to have a unit called Daltons today. So those are units of mass. An element is a substance that cannot be broken down into other substances by chemical reactions. So again, just think about your word elemental. It's something. It's the most basic way something can be. So an element is something that cannot be broken down into other substances by chemical reactions. And then when we think about matter and elements, and we think about atoms, and atoms are the smallest unit of matter that still retains the properties of an element, right? And so it's considered the fundamental unit of chemistry and physics. So we're going to talk a little bit about elements and atoms, and I'm going to skip a slide here and just show you, this is the table of elements, and we have about 92 elements that naturally occur, and there's several ways of organizing them. This was a particular way that has stuck for a long time, called the periodic table. Each element has a symbol. So H is for helium, hydrogen. He is for helium. If you look at this is more of a cartoony version of one, but if you look at a periodic table, at least it has several things on it. It has the symbol of the element, it has its atomic number, and its atomic mass. It may have other information on there too, but this is sort of the basics. Okay? Now, a lot of the symbols make sense. The C here is for carbon, right? N for nitrogen, O for oxygen, F for fluoride, fluorine, Ne for neon, right? There's aluminum, silicon, phosphorus, sulfur, chloride. All right, so it's the first letter, or maybe the first two letters, right? You have to kind of make up tricks, because if we use C for carbon, then we have to do something else for chloride. Same thing for silicon and sulfur. If we use S for sulfur, then something has to give for silicon. The things we care about for biology are kind of occurring over here. Quite a few of these are important for us. Then over on the left-hand side, the top of this first couple rows is important. And then kind of here in the middle, you'll see that we have some of these substances that are pretty important too. All right? So we don't really worry about much of the stuff here at the bottom at all. Now, I want to talk a little bit about the names, and this is kind of more of a triviality or something like that. But let's look at these two, because these are pretty important things in the end for us in biology: sodium and potassium. All right? And they have symbols that don't seem to have anything to do with their names in English. So that's where we're going to come back here. And the symbols come from the names of these elements in English, Latin, or German for the most part. And I want to talk about those two, sodium and potassium. So let's do potassium first. And our English word potassium comes from this word potash. And potash is the water-soluble remnants in the ash that's formed from burning terrestrial plant material. Right? Uh, you might think to yourself, why would I do that? Well, getting this potash is important for making soap, for making glass, and it can be used as a fertilizer. So, in fact, if you went to the um, hardware store or garden center, you would find potash being sold for fertilizer now. So, how someone figured this out, I have no idea. But if you take some wood or maybe some plants and burn them down to ash, what's really left there is potash. And the medieval Latin word for potash is kalium. And so now you've made the connection, right? Kalium starts with K. That word probably came from an Arabic word, kali, I hope, which means alkali, and we'll bring this word up again towards the end. Anyway, that word kalium, the Latin word for potash, is what gave us the symbol K. And for sodium, it's kind of a similar story. Soda is English word, and that in Latin Romance languages is some kind of derivation of natron. That is the name of a mixture of sodium carbonate and sodium bicarbonate, which we call sodium bicarbonate is in your kitchen possibly as baking soda. And that is the water-soluble part of the ash that's formed when you burn a marine plant or algae. All right? So because we have that word, we get from soda and natron, we get the words sodium and natrium. And from natrium, then we get that symbol Na for sodium. So again, looking at the periodic table, it would maybe be hard to figure out what some of these are, but they often make sense when you just kind of figure out what the word for that element is in a different language, especially medieval Latin or German. Okay, so let's talk about some of these other aspects here and what elements are important. In biology, there's basically four main elements that make up the vast majority of the substances, the matter that is involved in life. Right? And here you see this body of a human divided up and showing kind of not super proportional, but basically these compositions. And really, there's 1, 2, 3, 4 of them that make up the bulk of the mass of an organism. Oxygen is the most, it's heavy and takes up a lot of mass, so it's the biggest proportion. Oxygen, then carbon is second, so we have 65% oxygen, 18.5% of carbon, 9.5% hydrogen, and 3.3% nitrogen. So all these other elements make up just a very small proportion. If these all added together, give us 98.5% of the mass. We're left with these other elements. So some of these we mentioned, but others we haven't yet. Calcium, phosphorus, there's potassium, sulfur, sodium, chloride, and magnesium. We find these in different roles in different places in the cells of organisms, but they all play very important roles. But there's also a group of elements we call trace elements. And looking at this, you might, if you take a vitamin, like a multivitamin or something daily, now, or maybe in your future, you'll notice a lot of these things are kind of included. And these trace elements, they make up less than 0.1% of the mass of an organism. But again, they're pretty important. And some of these look kind of strange. They're really valuable in these very small amounts, but could be toxic in larger amounts, or maybe things that you would be surprised to find in your body. So perhaps chromium and copper, tin, and molybdenum seem strange to find in your body, these kind of metals. And a lot of these things that are here have, again, important roles. A lot of them are involved with molecules that we call enzymes. Iodine's important for making a hormone. Iron, as you may know, is used by your blood cells to help carry oxygen. So there's different roles that these play, but they're a small amount, but they're super important. So kind of three levels. We got the bulk, oxygen, carbon, hydrogen, nitrogen, and we're going to talk a lot about how these make what we call macromolecules tomorrow, and biochemistry. And then we have the less abundant elements, things like calcium, phosphorus, important for bone, potassium, sodium, and chloride, important for regulating the water levels and the salt content of your body. And then these trace elements, important particularly for functions of enzymes and some other things. So, fortunately, not all 92 are involved in our need to know about chemistry for biology. So let's get down and talk a little bit about atoms. So atoms, again, are the fundamental element particle of physics and chemistry. They're composed of yet smaller things, subatomic particles, right? The thing is that when you break an atom up into its subatomic particles, it loses. Those elements don't have the characteristics of the element, right? So it takes a whole atom to have all the characteristics of an element. There's three particles that we find in an atom. They are protons. Protons have a single positive charge. They have a mass of what we say 1 Dalton. And it's from the number of protons in an atom that we get that atomic number. Okay, so remember right above the C on that tile in the periodic table, there was a 6, and so carbon has 6 protons. There are electrons, which have a single negative charge, and there's the same number of electrons and protons, and so those charges balance each other out. So there's an atom, generally speaking, has no net charge. We'll talk about an exception to that. And then neutrons have a mass of about 1 Dalton, but they have no charge, so they're electrically neutral. So protons, neutrons, and electrons. The protons and neutrons are packed tightly together in the core of the atom in a thing we call the nucleus. We're going to see this word over and over again, nucleus. The word itself means nut. So we have an atomic nucleus. The cell is going to have a nucleus, and then we might find a couple other places where we use this word. So the mass number of an atom is the sum, that's what this symbol here means, the sum of its protons and neutrons. its atomic mass is about its mass number, but includes is an average of all its possible isotopes. What's an isotope? An isotope is an atom of an element with additional neutrons. Okay, so now just take a pause and think about it. It's the protons, right, that we use to get this atomic number, and maybe then is the critical number for determining what element something is, right? And most of the time, there's the same number of protons and neutrons, right? But some elements can have additional neutrons, and then we say that those are isotopes. So iso means the same. So they're the same element still, but they have these different masses. And so we have to take that into account when we do the atomic mass. And then, even though they don't they have very little mass, electrons do have some mass, so we have to take that into account too. Electrons are in constant motion around the nucleus, and often we kind of metaphorically talk about it as being a cloud of electrons, so, swirling around the nucleus at nearly the speed of light. And again, like I said, they have very little mass. It's about a 2,000th of a Dalton. So let's look at another tile from the periodic table. We'll look at helium. So this is like a little tile extracted from the periodic table, and we have our atomic number 2. That tells us that we have 2 protons, and then we can kind of go ahead and think about it. We're going to have 2 neutrons and 2 electrons as well. And then we see down here its mass number of 4.0026. I'm sorry, this is its atomic mass, 4.0026. And so we have the mass of the protons, the 2 neutrons gives us the 4, and then any isotopes and electrons, and here it's mostly electrons, give us this little bit that's tagged on there at the end, the 0026. Okay, so here's just to break down again: 2 protons, 2 neutrons, 2 electrons, with the protons and neutrons in the nucleus. So here's a little cartoon of the nucleus showing the 2 neutrons and the 2 protons, the protons with their positive charge. And then here are the 2 electrons. And maybe you've heard of this before. There's a principle from chemistry and physics called the Heisenberg uncertainty principle. That you can never really know where these electrons are, basically. When you try to measure them, you change what they're doing. So they're moving around very fast, managing not to collide with each other, and we often draw them sort of opposite each other just to make it easy, but they could be anywhere in this sphere at any time. Okay, and so and envision that not just going, you're looking at it in 2 dimensions, right? It's coming towards you, it's going away from you as well. So let's look at a couple other ways to display atoms. And so this is a different way. We can kind of draw the instead of the sphere, we can kind of just draw a circle around the nucleus and put the electrons there. And we often talk about the electrons as being in a shell. Okay, so this innermost shell holds 2 electrons, and this is our helium atom again. And again, we have our 2 positively charged protons, and they determine which element it is. How many there are is the determining factor for what the element is. And then the neutrons have no charge, and there's, again, 2 of them here for helium, and they determine the isotope. So if there were more, we'd have an isotope, but here we just have the 2, so we just have our normal element. And so there's our nucleus consisting of the protons and neutrons. And then we have these 2 electrons, in this case, with their negative charge, and electrons are what participate in chemical reactions. And we can get more shells of electrons, so some may have a second shell or a third shell, and we'll see that examples of that in a bit, and we'll talk more about it. But when we see those outermost shells, whatever the outermost shell is, that's the one that can have its electrons determine the chemical behavior and participate in chemical reactions, right? So each thing kind of is a determining factor, right, about how this element will behave and react. The protons determine which element it is, the electrons its chemical behavior, and the neutrons its isotope. Okay, just a couple more things before we take a little break and answer some questions. And we want to talk more about those isotopes. To be honest, they're not going to come up again a whole lot, but they are important for a couple different reasons. And in particular, we want to talk about isotopes of carbon. All right. So remember, an isotope is an element with a different number of neutrons. And carbon, this is carbon, so it has that atomic number of 6. That gives it 6 protons and 6 neutrons and 6 electrons. And if we look, we can see there's our nucleus with our protons and neutrons. And then here's that innermost shell of electrons orbit with 2 electrons in it. And then we need 4 more electrons to balance things out, and they're in the next shell. So there's a second shell here that holds 4 electrons. Now, what I want to tell you about this outer shell is it could, in theory, hold 8 electrons, and that's going to be important later. All right. So we get our kind of most abundant isotope. We call it carbon-12, right? That's the atomic mass number, or the total number of protons and neutrons. So carbon-12, and it has an atomic weight of about 12. Remember, plus we can get some additional decimals there for the sake of the isotope average. But we're kind of looking at not the periodic table kind of version of it, but just this particular isotope, right? So it's by far the most abundant. This, if you're going to find a carbon, it's going to most likely be this one, right? Almost 99%, not quite, but if we have one more neutron, right? So it can't really hardly even tell, but if we stuck another neutron in here, now we have 6 protons, 7 neutrons, and a mass of 13. Again, with some decimal points. We still have 6 electrons, and the neutron doesn't change the charge or anything because they're neutral, electrically neutral. So we just have a bigger mass. And carbon-13, as it turns out, is around 1% of all the carbon in the world, but it's also a fairly stable molecule, so we can use that sometimes to make measurements. There's some variations in different places and times how much carbon-13 there is around, and so it can be a useful thing to try to measure, even though it's a very small amount of something. The one that we might find more interesting in a way is carbon-14. Carbon-14 has 6 protons and 8 neutrons, so it has 2 additional neutrons. It has its atomic weight, up there at 14, with a little bit of extra stuff with the different kind of take into account the electrons and such. It is very, very rare as it goes. So 1 part per trillion. So you can't even do it as a percentage here. It would be such a small number. So there's not much of it around, but it is an unstable molecule, and eventually it will give off a neutron or two and decay back into carbon 13 or carbon 14, which are more stable, right? So, or it could give off. We're going to talk in a moment about different particles. It could give off, a little helium atom, and that would change what element this was. So there's a feature of something we call that when it gives off these particles, we call it radioactive. And when we talk about something that's radioactive, we talk about it having a half-life, and that's the amount it takes for half of this to decay to a more stable molecule that's not radioactive, or atom, sorry. And for carbon 14, its half-life is 5,730 years. That's a very long half-life. It takes a long time for it to happen. So even though it's unstable, it's a slow process. Now, just in general, we can take advantage of radioactivity for a couple of different reasons. We can, not so much from the things like carbon, but from some of the things lower on the periodic table, the elements lower on the periodic table, like uranium. We can use those radioactive isotopes to generate energy. So when they decay back to a more stable molecule, they release some energy, and we can kind of try to capture that. And that's what nuclear power is all about. This is the nuclear power plant in Limerick, and it's using the decay of radioactive material to generate heat, and then using that heat to generate electricity, and harnessing that, and some might be even providing us with electricity as we're talking now. We can use radioactivity in research and diagnosis, so we can use it carefully to get different kinds of body imaging done. We can use it for various other ways of using it for research. There's so many ways I don't even can't really list them in anything for you. It's just a myriad of ways. We can also use them for treatment. So you might see there's this little section in the textbook, or you might have heard of it before, where you might use radioactivity to treat particular cancers. And so people often get chemotherapy as well as radiotherapy for cancer treatment. Now, radioactivity is often the cause of cancer for certain cancers, especially you think of skin cancer, but some others, and it's because these particles that are released during the decay process can be what we call ionizing, and that can have effects on molecules in the body. And so here, this little squiggly lines are the radiation, and they can get to a cell, and then within the cell, they can cause breakage of the DNA, which can lead to mutations, and those mutations can lead to unregulated growth, which we call a tumor, and so that can produce cancer. And our bodies have evolved to kind of protect us from that to a large extent, but it still can happen, especially when this, so that's why you have to be very careful when you're out in the sun a lot. You might want to be careful about wearing sunscreen so that you don't get skin cancer. All right. Just a couple more slides real fast. I'm kind of talking too slow. I'm sorry about that. But we got the different kind of particles that can be released by radioactive elements, isotopes. Alpha particles, those are basically a helium nucleus, so not an helium atom, but just its nucleus, with 2 protons and 2 electrons, no electron. 2 protons, 2 neutrons, no electrons. If we release just an electron, we call that a beta particle. Alpha particles really don't travel very far from the radioactive substance, and they also can't really penetrate any sort of barrier whatsoever. Beta particles can travel a little bit further. So alpha particles about an inch, beta particles about a meter or a yard. And very thin barriers they might be able to penetrate, but they often aren't really able to penetrate into your, say, skin. And then gamma particles. Um, and a gamma particle is a photon, and this is a packet, elemental, or a fundamental unit of light. And these can travel very long distances, and also are able to penetrate fairly deeply into biological tissues. We can protect ourselves from gamma radiation using things like lead sheets or cement, thick layers of cement. So these are definitely, but all of them can cause problems for biology. So but you might hear these terms. So alpha, beta, and gamma particles, different elements. With alpha being the nucleus of a helium atom, beta being an electron, and gamma being a photon. Now, I want to talk about that carbon 14. One last little slide here, and then we'll take a little break. So there's super small amount of carbon 14 in the world, but there's some. And during the course of organism's life, it'll incorporate some of that carbon 14 into its body. Here are the pictures of a mouse. The mouse ate some plants. The plants absorbed carbon 14 from the atmosphere, incorporated it into their structures. The mouse then ate those plants, and some of that carbon 14 ended up in its body. And of course, all throughout the life, there's carbon 14 that's kind of slowly decaying away, but the mouse is always constantly eating and renewing the carbon 14 that's in its body. And that keeps happening until it dies. When the animal, in this case, or the organism, dies, then there's a certain amount of carbon 14 that's there, and over many thousands of years, it'll become less and less and less as this carbon 14 decays and gives off its radioactive particles and becomes carbon 12. So here we're looking at a ratio of carbon 14 to carbon 12. And we're just kind of normalizing it to the moment the animal died. So it's a percentage, right, and of the ratio. So when it died, there's 100%, of the carbon 14 that it's going to have. And then now, say this animal died a long time ago. I think this is more useful for fossils than if you found a mouse in your mousetrap. And we dig up the fossil, the bones, and we're able to measure how much carbon 14 is still there. Well, it's going to exponentially decrease over time. But as long as the animal is, not too old, so that there's no carbon 14 whatsoever, we can kind of measure the amount of carbon 14 and then figure out how long ago the animal died by looking at the amount of the carbon 14 in its body still. All right. I am going to stop there and switch back to being live with me. And I will ask if you have any questions. Hopefully we're keeping it pretty simple, but it is 8 o'clock in the morning, so, and I haven't had my coffee yet. I'm sure I might have said something confusing. Of course, unlike Zoom, you can't speak up. You have to go to the chat. All right. All right. Well, It seems like we didn't have any questions, so I'm just going to go ahead and move forward and go back to the slides. So here's our atom again. Uh, Again, just going to remind you a couple things. The protons are what determine which element we have, the number of protons. So in this case, 2 protons gives us atom of the element helium. If we had 6 protons, that would give us the element carbon. The neutrons tell us what isotope we have. So if we have just the base number, then we're looking at the element itself, and then we usually give that isotope a number that's the sum of the protons and neutrons that are in the nucleus. And then we have the electrons, which are going to determine how an element participates in chemical reactions. So we're basically going to talk about reactions that build other things or that break things down overall. But again, we kind of do have to deal with a little bit more terminology. And one of the words that we need to kind of add to our list here is compounds. So elements can be combined to form compounds. And a compound is a substance that contains 2 or more elements in a fixed ratio. Now, I want to add another word here, so you might want to write this one down: molecule. Okay. A molecule is a substance that has 2 or more atoms, right? So, for instance, oxygen can form a molecule with itself, right? We can have 2 oxygens together, forming a molecule of oxygen. And so, a compound is a subset of molecules that have 2 or more elements in them. Now, as we go into the next lecture on biochemistry, we're going to be talking a lot about compounds, and I'm going to use the word molecule. It's just our convention. All right. So understand that there's sort of a real definition for each of those that makes compounds a subset of molecules, but then I may use molecule in that kind of improper way to refer to anything that's got more than one atom in it. All right. Hydrogen and oxygen, say, can combine. They can combine in multiple ways, but one way we can combine them is with 2 hydrogens and 1 oxygen to form water. Okay. So our elements are hydrogen and oxygen, and we get out of that a compound called water. We can take carbon and oxygen and combine them. We can combine them in a 1-to-1 ratio and get carbon monoxide, a deadly poison. Or we can get carbon dioxide, where we have a 1-to-2 ratio, and that is the end product of metabolism to a large extent. We can have more than 2 things, so we can have more than 2 elements. So we can have hydrogen, oxygen, and carbon, and again, we can combine these in many, many different ways, but we can get bicarbonate and carbonic acid out of the deal. So one type of reaction is where we form bonds between these different elements to form compounds. And so let's talk about what a chemical bond is. A chemical bond well, remember that it's the electrons in the outermost shell of an element that determine its chemical properties. And so chemical reactions occur when electrons are transferred or shared from one atom to another to form or break chemical bonds. And chemical bonds then are linkages, between atoms that help form compounds or molecules. There's three types that we care about the most: covalent chemical bonds, where the electrons are shared, so electron pairs in the outermost orbit are shared, forming a very strong bond. Intermediate in strength are ionic chemical bonds, and here electron is transferred from one atom to another, leaving one with a net positive charge and the other with a net negative charge. And we'll talk more about this in a moment. And then hydrogen bonds. So this is unfortunate, but hydrogen's the name of an element and the name of a bond. So hydrogen bonds are a weak attraction between polar covalent bonds with hydrogen. So there's a special type of covalent bond that we call a polar bond, and I'm just going to wait and tell you about that in a little bit. And those covalent polar bonds can interact with hydrogen atoms to form this weak attraction that we call a hydrogen bond. And while hydrogen bonds are weak, they're super important for at least two things. They're super important in water and giving water its special characteristics. And at least casually, you must know that water is super important for life. You need to drink a certain amount every day. You know that when we look for life on other planets, one of the first things we look for is there water? So water is super critical for life, and hydrogen bonding in water is one of the things that gives it its special properties. The other place where hydrogen bonds come into play that are very important is when we're talking about DNA and RNA, and so it's going to come up again there. Hydrogen bonds. Okay, I'll talk more about it in a few minutes though. So let's also just talk about some different ways to represent compounds. So far we've kind of used a little bit of this method, the molecular formula. With the molecular formula, we just use the letters from the table of elements with the symbols. So C for carbon, H for hydrogen, and O for oxygen. And then we can use a subscript number for indicating how many there are. So this is, we'd say, a carbon, one carbon, two hydrogens, and an oxygen. And this is a molecule called formaldehyde. And we can represent formaldehyde in a couple of different ways. Here we're showing something kind of like a cartoon of the atom with the nucleus. We're not drawing each individual proton and neutron. The nucleus and its inner shell and its outer shell. And we're not showing all the electrons drawn in. We're just showing the shells and then the electrons that are being shared between the two atoms. So here's oxygen, carbon, and two hydrogens. Let's look at that hydrogen there. So each hydrogen has a single electron, and remember carbon's outer shell had 4, so we can kind of arbitrarily say that one, and these two belong to carbon, and so the other things belong to these other elements. And so here carbon and hydrogen are sharing this pair of electrons. This hydrogen and this carbon are sharing this pair of electrons, and we call those single bonds. And then up here we have the oxygen and the carbon sharing uh, two pairs of electrons. We call that a double bond, and that's even a stronger type of covalent bond. Now, remember, what's important here is uh, oxygen in this outer ring had 6 electrons. By sharing with carbon, it fills that outer orbit with 8 electrons. Carbon had 4 electrons in its outer shell, so it gets 2 more from oxygen, and then it gets 1 each from the hydrogens to make its outer shell have 8 and filled. Okay? So you don't want to anthropomorphize it too much by using this language, but the atoms, there's they're going to try to fill those outer shells one way or another, and one way they can do that is by forming bonds. And so you just, to see whether a bond will form, you just have to see if there's some kind of compatibility in terms of that possibility of sharing electrons. So we can get less worried. We can kind of just assume we remember everything about the electrons, and we can use these other kind of ways of representing compounds. A structural formula, we just draw the symbol, 2 lines for a double bond, 1 line for a single bond. So these 2 things are equivalent ways to represent formaldehyde. We can have a space-filling model, so now we're just thinking about that outer shell of electrons and kind of the volume of the atom in that case. And so we have our red oxygen, our black carbon, and you can see that's the case here too, the red and black. So we kind of assign certain colors to certain elements, and that way we don't have to write so much details. And so the hydrogens here are white, and that gives us that space-filling model. And then we can also have this ball and stick model, and this is particularly useful if you get a kit. You can get a kit with little plastic balls and little plastic sticks that represent the different elements, and you can build the molecules with them. So that's kind of where this comes from for drawing too. So let's think about water and the chemical bonds there. We have our oxygen with its 2 innermost electrons. They don't participate in the chemical bond formation. And then we have its outer ring, which had 6, so there's 2 there, there's 2 there, and then it's sharing one of the other 2 with each with a different hydrogen atom. And so again, that kind of fills this outer ring, outer orbit of electrons with 8 electrons for the oxygen, and gives the inner ring of the hydrogen 2 electrons. And remember, these electrons are moving really fast, so that they're basically everywhere at the same time almost, right? So it makes those outer rings filled, and that's just a stable place for these elements to be. So that is our water molecule. All right? And so now we can represent it. There's the ball and stick, where we have our oxygen and then a stick leading to each hydrogen, with the stick representing a covalent bond. And here's the space-filled model of a water molecule. And this is where we want to talk about polar covalent bonds. So in some covalent bonds, like the bonds between carbon and hydrogen, the electrons are evenly or equally distributed between the 2 atoms. In other covalent bonds, because of certain properties of certain elements, the electrons are not evenly shared between the atoms. And in water, that's the case. So here we have the space-filled model showing our kind of 2 hydrogens and our 1 oxygen. And in this case, because of the nature of oxygen, it tends to hoard the electrons. The electrons spend more time orbiting the oxygen than they do orbiting the hydrogens. Now remember then that that's going to mean that oxygen often has 8 electrons associated with it instead of 6. And that makes the oxygen slightly negative. Okay, so electrically negative. And because the hydrogens do not have those electrons associated with them, their protons are kind of there bare then, and they become slightly positive, right? So we get this polar, which means it has different sides. We have a positive side on the hydrogens and a negative side at the oxygen, right? And again, this is going to be important for the properties of water and for forming hydrogen bonds. But before we talk about that, let's go on and talk about that. We talked about covalent bonds then, and then we had that special case of a polar covalent bond. And now we want to talk about ionic bonds. So here we have 2 atoms of two different elements, a sodium atom and a chloride atom. And here you can see now in this case we have 3 electron shells. So we have an inner shell with 2, I'm looking at the chloride now, 2 electrons, and then we have a middle shell with 8, and then we have an outer shell with 7. Now look at sodium. It has an inner shell of 2, it has a middle shell of 8, so that's nice and stable. But its outer shell only has 1 electron. Now, these atoms could theoretically participate in a covalent bond, but what happens in this case instead is that sodium just transfers its lone electron in that shell, outermost shell, to chloride. So now that outer shell is gone from sodium, and it's got this nice stable electron configuration, and it's lost an electron, so it has a net positive charge. So that's what we look at, right? It goes from this to this. So 2 inner electrons, 8 outer electrons, and 1 more proton than electrons, so a positive charge. And at the same time, chloride has now gained that electron, and it's now has a stable outer shell with 8 electrons in it, but it has an extra electron, so it has a net negative charge. And so there's our middle, and now our 8 in our outer. So, and what we get from that is this compound that's formed by forming an ionic bond called sodium chloride. And that is table salt. It's also important in the fluids of our body, and of course it's a main component of the ocean. And what holds these together isn't that shared electron or 2 between the molecules, but it's the nuclear charges. So kind of like the 2 ends of a magnet, drawing the 2 ions, now we call these, together. So an ion is an atom with a charge, and so we have a sodium ion and a chloride ion. And just to kind of give you another term here, we call a positively charged ion a cation, C-A-T-I-O-N, and a negatively charged ion an anion, A-N-I-O-N. And if you do anything with electricity, those words will make sense to you. But so we have a sodium cation and a chloride anion attracted by their and held together by the charges of their nucleus or nuclei, as opposed to through shared outer shell electrons. Okay, so you get the difference between covalent bond and ionic bond, I hope, and that you see why maybe the ionic bond might be a little weaker. Let's look at another example here of a couple of ions, and just again, lithium had one more shell with just a single electron in it, and fluoride had in its second shell only 7 electrons. And so lithium donated its outer shell electron to fluoride, and now we get these two ions, the lithium ion, which is the cation, and the fluoride ion, which is the anion. And it's just that charge in the nuclei that are holding these guys in kind of association with each other in a bond for lithium fluoride, sorry. All right, let's talk about hydrogen bonds. So here's our space-filled model of water. These occur again in other molecules besides water. We're going to see them with other molecules down the road, but water is the one we're going to talk about today. And so remember, we have these polarities, so that the hydrogen end of a water molecule has a net positive charge, and the oxygen end has a net negative charge. And just like in an ionic bond, that those opposite charges attract each other. The trick here is that these are weaker charges. So the oxygen is only slightly negative, and the hydrogen are only slightly positive. Okay, so they're weaker bonds than we have where we have an ionic bond, and so we form this orientation and attraction of water molecules to each other, such that hydrogens of one water molecule are oriented towards and attracted towards the oxygens of another oxygen molecule, and the oxygens are attracted to the hydrogens. And again, because of this weak traction, which we call a hydrogen bond, water has some special properties, and we want to talk a little bit about those before we move on to talk about chemical reactions. So, like like elements, compounds can also exist in their different states. So, liquid, solid, and gas. And this is just a picture showing, water as a liquid, a solid's snow, and I'm sure there's some ice along the edge of the lake here, and then as vapor up in the clouds. So as a gas. And one of the properties of water that you get from those hydrogen bonds is a property we call cohesion. And so here, as the water maybe is being drawn up along a surface, the leading water molecule is, its hydrogen here is in a hydrogen bond with the oxygen molecule below it, in the water below it, and then on and on, so that these waters, you can't, it's hard to separate one compound, one molecule of water from another, because of these hydrogen bonds. And this is an important property for a couple different reasons. Cohesion is one of the ways we can kind of move water places that it would be hard to go. So here's a picture of a tree, and the tree has roots that go deep in the ground and draw water in, and then out at the top of the tree where the leaves are, some water is evaporating away that needs to be replenished and replaced. And so we need to get water from down in the ground, in the roots, and up to the leaves, and that's has to fight against gravity, right? So, but within the plant, there are special tubes that conduct water to allow the water to move through the plant. And the key thing about how the water is moving and able to fight gravity to get up to the leaves is due to this property called cohesion, right? There's a couple other things in terms of that participate here, but cohesion is really important for it to happen. Another place you can kind of see and one of the special properties of water is its is surface tension. And this one, maybe is a more trivial example, but on the surface of the water, all those water molecules are oriented towards each other, forming, sort of a little bit of a sheet. And it's not a super strong sheet, but again, if you've ever done a belly flop, it's not nothing. And here what we're seeing is this very lightweight spider is able to kind of crawl across the surface of the water using that surface tension so that it doesn't sink in. Now, it doesn't take much of a disruption or a mistake on the part of the spider to have it sink in, but as long as it's careful and scurrying across the water surface, it'll be able to do it. So surface tension is a lot like cohesion, but it's happening just at an interface between the water and another thing like air. So a couple more properties. Water, as it transitions from one state to another, and especially when it's going from liquid into gas, gives off or is able to allow this kind of cooling effect. So as water evaporates, energy is dissipated, and we get this cooling effect. And so that's important for organisms that live in places where it's hot, and so we have adapted to this. This is why we sweat. Those, again, because of the hydrogen bonds, it does resist these transitions from state, so it does provide some and it's able to absorb a lot of heat. So bodies of water provide for environmental stabilization. And again, you might notice this if you ever go to the shore. The temperature difference at the shore is less than it is even here in Westchester. And if you were to go off to Indiana or Ohio or out to the desert Southwest, you'd see much bigger temperature fluctuations over the course of the day. So when we live near a large body of water, and it can be the ocean, but it could even be a lake could have this effect, we get some environmental stabilization. And then the one that's important here for our discussion of chemical reactions in biology is that it acts as what we call a universal solvent. So because it has these complex properties, but also in part because of its polarity, it's able to dissolve a wide variety of different other substances. So obviously not everything, so it's universal is a little bit of a overstatement, but water dissolves almost everything, and we're going to talk about that, I guess, a little bit more in a moment. But this was another place I wanted to kind of stop and see if I can answer any questions. So let's take a pause here and let me pull up the questions. So we had the what are the definitions of cation and anion? Cation is a positively charged ion. I'll type it too. And an anion is a negatively charged ion. Okay, so you want to say it a different way. A cation is an ion with a net positive charge, and an anion is an ion with a net negative charge. Um, any other questions? Well, if I think then I'll just go ahead and move on to our last section here. Um, so we want to talk about chemical reactions finally, and then we'll end it with a little bit of a discussion of pH. And what we looked at earlier, we looked at maybe the formation of some compounds. So those were reactions. And we can also break down compounds by breaking chemical bonds. And those are reactions as well. So a, a, a reaction is a change in the composition of matter. So that delta there means a change in the chemical composition of matter. And it has kind of two parts to it. We have reactants, so things that we start with, and then products, the things that we end with, right? So here our reactant is a compound called hydrogen peroxide, and there's only one of them here in the picture, but we're imagining we have two of them. Okay, so one hydrogen peroxide reacts with the other hydrogen peroxide as reactants, and then we have this arrow shows the progress of the reaction to its products. And what we get out of that reaction between two hydrogen peroxides is two waters and a oxygen molecule. Okay, and if you add things up, you can see it works out. So we have 1, 2, 3, 4, four oxygens, and we had 1, 2, 3, 4 because we had two hydrogen peroxides. So we had 4 oxygens. So the numbers should stay the same, right? We had 2 hydrogens, but we had 2 of them, so we had 4 altogether, and then we ended up here with 1, 2, 3, 4. All right. So reactants are the starting materials for a reaction. The products are the ending materials for a reaction. And what we get is a change in the composition. So we go from a compound of hydrogen peroxide to water and oxygen. So here's some other similar types of reactions where one compound is going to break down into something else, and in this case we're going to have some ions involved. So we're going from something uncharged to something charged. And I've kind of written this in a certain way, and what I'm going to explain to you. I'm going to start down here with the water at the bottom. So here's our good friend water, 2 hydrogens and an oxygen. And when we have pure water, a certain amount will break down into a hydroxide ion, an anion, and hydrogen ion, a cation. And I've drawn it here with this special kind of arrow, so it goes this way, right? But what happens is that when we start with a lot of water molecules, a certain amount of it will break down into hydrogen and hydrogen hydroxide ions. But eventually these start to build up, and they can go back to form more water. And we get into a state that we call a dynamic equilibrium. So water's constantly being broken down into the ions, and the ions are constantly reforming water, so that the concentrations don't really change much once we've reached that state. Now we can do things like we can use one of these in something and take it away, and then that keeps driving the reaction in one direction. All right? So that's something we call the law of mass action. We start with a lot of reactant. It drives the reaction towards the products. Okay? And that's the law of mass action. And then eventually we can get to a state we call a dynamic equilibrium, where the rates of the forward and the backward reaction are happening at the same rate. Now, not every reaction has both directions, but a lot of biological ones do. Kim asked a question, but I'm going to wait and answer that at the end, I think. So bear with me, Kim. Or I'm sorry. I don't have my glasses on, so I cannot read the name very well. I apologize. Let me just explain a couple more things, and then we can kind of come back to it. So sodium chloride here, again, this goes almost all the way completely to sodium ions and chloride ions. This one up here, this is carbonic acid. Again, don't worry about it too much, but this is a super important reaction, so I'm going to show it to you probably a few times. But carbonic acid can break down into bicarbonate and hydrogen. And this is an important reaction for maintaining certain type of balance in your body. So this reaction happens in your blood. It happens in, it's important for breathing. It's important for forming urine. So there's many parts of the body where this reaction is happening, and it's super important. And I kind of want to go back to that law of mass action a little bit here. So what happens if we, from some other source, we add in some more hydrogen ions? Well, some of those hydrogen ions will combine with the bicarbonate to form more carbonic acid, and shift the direction this way. So we can, if we add something to the system, we can shift the dynamic equilibrium. All right. And so that's going to allow this molecule, this carbonic acid, to have a special property, and I'm going to tell you more about it in a later, but I just want to highlight it here and so you have it in your mind, okay? It means that this carbonic acid can act as something we call a buffer, right? So, besides being important in your body, it's also important in the environment. And so that's what I want to show you in this slide. This reaction, there's the carbonic acid, and so you can imagine the other parts of it, right, where it breaks down into bicarbonate and hydrogen ions, is involved in a process called ocean acidification that's happening due to climate change. And so as we get increased carbon dioxides in the atmosphere, carbon dioxide is absorbed into the water of the oceans, and this can happen in lakes too, freshwater or saltwater. And that carbon dioxide combines with water molecules to form the carbonic acid. And then the carbonic acid can go on to form bicarbonate and hydrogen ions. And hydrogen ions are the hallmark of something we call an acid, something that puts those into solution. And so that's why we call this carbonic acid. And that increase in hydrogen ions changes this property of the water that we call its pH. And we're going to explain that a little bit more in a moment. But that affects all the organisms living in the ocean, and especially certain things that are shown in this picture, like corals, are very sensitive to those changes in pH. And we can go from having very lush, diverse coral reefs to them being completely just dead due to this ocean acidification process that's happening. So one of the things that we talk about different different greenhouse gases, but carbon dioxide. One of the reasons why it's dangerous is because of this process. Okay, so more terminology. When we're thinking about chemical reactions in an organism, we're thinking of chemical reactions that happen in solutions. So we need to talk about what a solution is. A solution is a liquid consisting of a homogeneous mixture of two or more substances. So something like, say, water and sodium chloride would be a salt solution. Okay. An aqueous solution is a solution that has water as its solvent. And so that's, again, aqueous solutions are kind of the most relevant for biology. And then a solvent is the dissolving agent in a solution. So think of just dissolving something coming apart and becoming homogeneously distributed through it. That the thing that's holding that thing, which we're going to name next, is the solvent. And the thing that's being dissolved and distributed and surrounded by the water or the solvent, whatever it happens to be, that we call the solute. Okay? So again, just definitions for different things so we can have a common language here. Here's our water reaction again, because now we're going to shift and talk about pH. So we'll talk some more about reactions tomorrow when we talk about the formation of macromolecules and the breakdown of macromolecules that are important for biology. And so hopefully this, though, sets the stage for that. And so now let's talk about pH a little bit, because it's another important thing. So here's our water molecule, and like I said, a small amount of it will break down into hydroxide ions and hydrogen ions. So how do you know which of these is positive and negatively charged? So give me a second here to put the... So remember, we have a single proton. Oops, I can't draw very well. There we go. There's our single proton in our hydrogen atom, and then it has a single electron in its orbit, right? So its atomic number is 1, and it has one proton and one neutron and one electron. And so when a hydrogen atom is going, remember, it wants to kind of have 2 here in its outer shell. And thinking back to oxygen likes to have, it has 6 in its outer shell, and it likes to have that full. So here the hydroxide ion provides that hydrogen in a covalent bond, provides one of the electrons, and this electron, the sole one that's surrounding the nucleus of the hydrogen, will kind of transfer over to the hydroxide oxygen, and now it has 8 in its outer shell, and rather than having just 1, this one has 0. So it always wants, these shells try to be filled. So that's kind of how you can figure out which way the charge will go. You look for what might happen to either empty a shell or fill a shell. the outermost shell of a atom or compound. So maybe I can kind of come up with a little exercise that I can post up on D2L for you guys to practice with that. So when we're thinking about pH, we look at we're thinking about how much of this hydrogen ion is present. And in normal water, we call it a neutral solution because there's an equal number of hydrogens and hydroxide ions. And, if we can do something, if something happens that shifts things around so that we add hydrogen ions, we might put something else in the water, or we might do some other change that causes there to be more hydrogen ions in the water. Then we call that an acidic solution. And if we have fewer hydrogen ions, so there's more hydroxides than hydrogen ions here, we call that a basic solution. So just some definitions, right? An acid is a chemical compound that releases hydrogen into a solution. So I have hydrochloric acid here, carbonic acid. Obviously, anything with acid in its name, probably going to do this. So that's just the simple definition. It releases a hydrogen ion into a solution. A base is a compound that accepts a hydrogen ion and removes it from solution. And my example here is sodium hydroxide. This dissociates right into a sodium ion and a hydroxide ion, and then a hydroxide ion can absorb and form water and take that proton, the hydrogen ion out of solution. And then here's that definition of a buffer. A buffer is a substance that retards a change in pH. pH is just the concentration of hydrogen ions by accepting hydrogen ions when that ion is in excess and donating them when they're depleted. All right. So it's by following the law of mass action, the buffer can either pull in a hydrogen ion or give up a hydrogen ion to keep the concentration at a stable level. And different buffers will have different levels at which they're effective. So we have a scale of pH that goes from a pH of 7 to a pH of 14 at its most basic, and a pH of 0 at its most acidic. And what we're looking at here is a way of representing the concentration of the hydrogen ion. So this little square bracket, right? You see it here, you see it here. This square bracket means concentration of. And because this scale is fairly large, we're using a logarithmic scale. You don't have to be too worried about that. I'm going to try, I hope this kind of works out here, to show you where that comes from. Sorry, my mouse is going haywire. There we go. So what does that number pH 7 mean? So we have a concentration of hydrogen ions that is 1, I think I have to get the thing each time here, times I'm sorry, this is very crude, to the minus 7. All right? So just bear with me and think about this. Okay, so let's do it the opposite way. Let's say it was 10 to the 7th, which would be, up here, or I'm sorry, well, it would be way off the chart. So 10 to the 7th. Let's go back one. 10 to the 6th, right? 10 to the 6th is a million. So if the concentration was pH negative 6, that would be what we're looking at, right? A million whatever concentration units we're talking about. So 10 to the 7th would be 10 million. So 10 to the minus 7 is um, uh, uh, 10 millionth. All right. So a 1 with 7 zeros in front of it. So it's a very small number. And likewise, this would be 10 to the minus 14th, so an even smaller number. And 10 to the minus 0 is 1, right? So that's a lot of hydrogen ions that we have down here at the very bottom. Very few of them up here at the top, and here in the middle, this middle number. So pH, I don't know why it's giving, not holding on to it, but P, yeah, that's tedious. pH is the negative log. I'm not going to try to write that, I'm sorry. It's the negative log of the concentration of the hydrogen ions. So that's where those numbers kind of come from. All right. So, what's important for you to know, just realize that it's a very small number, but still something that we can measure, and that we have this range from 0 to 14, with 7 being right dead center in the middle. So let's think about the pH of some common things that you might find around the house. So in theory, pure water should have a pH of about 7. And let's go up from there. So things like blood in your body tends to be a little bit more basic. So it has a little bit higher pH number here. But remember, that's a smaller number. So a bigger number in the pH scale is a smaller number of hydrogen ions in the solution. So it tends to be a little bit more basic at 7.3, 7.5, something like that. Seawater, 8.5. Milk of magnesia, not sure any of you guys know what that is, but it's something people take for ailments like heartburn or indigestion sometimes. Getting here between 10 and 11. Ammonia, up over closer to 12. Household bleach up close to 13. Oven cleaner getting even closer to 14. So here's these things we use around the house for cleaning, right? Oven cleaner, bleach, and ammonia, all in the very basic range or end of the pH scale. What's even more interesting is what's on the acidic side, I think. So blood tends to be a bit more acidic, and it has a large range. Urine tends to be a bit more acidic. It has a large range over which it's normal, but typically kind of just mildly acidic. Coffee is around 5, and tomato juice down there around 4, so pretty acidic. We tend to like to drink acidic things. Grapefruit juice and soft drinks like Coke and Dr. Pepper are acidic, and if you look at the ingredients, you'll see why. Carbonic acid's there as one of the main ingredients, so that brings it down to pH 3. Lemon juice, almost a pH of 2, down there with stomach acid, which is a very acidic thing. Again, close to pH 2, and then we get into kind of things like battery acid, which are down here close to pH of 1. So cleaning products up there in the basic region, and lovely beverages down here in the acidic region. Although you might use things that are in the acidic region for cleaning too. You might use lemon juice for cleaning, or you might use acetic acid vinegar. Would be slightly acidic, and that you might use for cleaning too. So pH is going to be, again, we're going to kind of come up and talk about it in relative occasionally. So I just kind of want to give you that general idea of what pH is all about, and then I guess that sets the stage now, and we're ready to talk about other molecules. I realize I've run over time. I'm sorry about that. I'll go ahead and stop now and ask if there's any more questions, but if not, we can let you go. Yeah, go ahead, Zach, and ask. Off topic is fine. Lab is relevant. Yeah, so Zach's asking a question about lab, and so right, so by the lectures and the labs do go together. I haven't necessarily assigned them. I've tried to assign them so they more or less match up. Although, like, I made Lab One available yesterday, but it probably wouldn't have made sense to do it till after today. Um, so I've tried to line them up, but I've also want to give you time, I guess, to do them. So, um, but so for now, like if you've read uh, the intro chapter, uh, you should be, and I think the chemistry chapter, then you should be good for Lab One. Um, I will. Let me just double check, Zach. I'm sorry because I'm getting fuzzy on how the labs broke up for the first couple labs, and I'll put an announcement up on D2L for. I'm sorry, I just am spacing out on your answer there. Stephanie's asking about environmental stabilization, and yeah, it's really about. I mean, it has a couple of different effects, but uh, you know, the water has a great capacity to absorb heat, and and without changing its temperature too much, and partly it's just because the stabilization provided by those chemical bonds, the hydrogen bonds. So heat basically is molecular motion, and so the hydrogen bonds between water molecules dampens that motion. So that allows the water to be a stable environment itself. So organisms that live in the oceans tend to experience relatively little change in temperature. And it's partly why you hear about then these very small changes in temperature of the water, why they're so catastrophic. The organisms that live in the oceans are not adapted to living with wide temperature changes. They're used to a relatively constant and have evolved to live in relatively constant temperature conditions in the water. And so that's going to be true for any large body of water. And I mean, just I mean, I hope. I mean, I'm going to go make coffee. One of the reasons it takes so long to boil water to is because of this, right? Property of it. Now, the other effect, though, that water then can have an effect on the land near large bodies of water. Um, and so, uh, living near the Great Lakes or living near an ocean will lead to some stabilization um, especially of temperature in the environment. Other things like the humidity and some other things are also maybe made more stable, but the temperature is really the key one. So when we say environmental stabilization, it's primarily about the temperature. Does that make sense? And thanks. So yeah, lab one is mostly about chapter two. Someone has chimed in. I should do this with my glasses on. I apologize. I can't see all the names. So the instructions for accessing uh, Pearson are in an announcement on D2L. So you go to D2L and there's an announcement there, and also in the content area there's a instruction sheet that you can download or read, and that gives you the instructions on how to get to registered with Pearson and register it with the class, and then the on Pearson over on the left hand side once you're in is where you'll find connections to the textbook and the assignments, and so that's where you should see them. And then someone is asking, do we have another lab this week? Yeah, there's another one. It'll go live tomorrow, and then you'll have I might have even given you 3 days to do that one, so you could wait and do it over the weekend. But the other lab goes live tomorrow, and partly that's because you need to hear the biochemistry lecture to do it. I think. So you can look at the schedule. The schedule has when the labs will be available, and that's more reliable than asking me probably. And so the schedule's in the syllabus. I'll put the schedule up independently in the announcements too, so that it's there to see, so you don't have to necessarily thumb through the syllabus every time. Anything else? I'm sorry. I'm sorry we ran over. This is I'm kind of learning how to do this. My so, but I think this might work out better for everybody than the zooming was. So thanks for coming. Thanks for being patient, and I'll try to get some of these things filled in the blanks for you on D2L. All right. I One last thing. I don't know if it'll be the same link or a new link tomorrow. So, like I said, I'm still in the learning curve. So we'll find out. But so you might check D2L or your email in the morning to see if the link is the same. All right. Thanks a lot, and we'll see you tomorrow.